Hello everyone. In the previous module, we discussed the conservation laws that govern a nuclear reaction and also the Q value, how to calculate the Q value from the masses of the nuclei. Q value could be positive or negative, and accordingly they are called as exoergic and endoergic. Now we will discuss the energetics of nuclear reactions, particularly what is that energy that is actually available for inducing the nuclear reactions, that is called as the energy available in center of mass system, and also the kinematics of the nuclear reactions, whereby you can in fact calculate the energy and the of a particular reaction product at a particular angle. So that will be the main focus of the particular lecture. So let us discuss the kinematics of a nuclear reaction. We will set up the equation which we will solve to find out the energy of the ejectile as a function of angle and energy of the projectile. So we will see here we have the projectile of mass m1 and energy E1, the kinetic energy E1, bombarding a target which is at rest, E2 equal to 0. So the target is stationary in the here, and then it can form a compound nucleus, composite nucleus, or a compound nucleus. We will discuss the compound nucleus in more details in subsequent lectures. So MC is the composite, M1 plus M2 will form a compound nucleus. It may not form a compound nucleus, but for the time being we'll say it's a composite nucleus. And after this reaction, then you have an ejectile formed of mass M3, kinetic energy E3 emitted at angle theta, and the heavy residue of mass M4, kinetic energy E4 emitted at angle phi. So now we use the conservation laws to determine a relationship between E3, a function of E1 and theta. So that is the problem, that if you know the projectile and its energy hitting a target, then at a particular angle theta, what is the energy of the projectile for a particular energy of the projectile. Once we set up this equation, then for any reaction, in fact it is independent of the reaction mechanism, we can calculate at a, suppose you are putting a detector at a particular angle, you can know what is the energy of the ejectile. So that is the purpose of this reaction, and there are many corollaries of this derivation which may become apparent subsequently. So let us set up the equation for the conservation of mass and energy, which we derived in the previous lecture. So M1 plus E1 is the mass and energy of the projectile, plus M2 target is stationary, so E2 equal to 0. So M1 plus E1 plus M2 equal to M3 plus E3 plus M4 plus E4. So this is the conservation of mass and energy before and after the reaction. So now we can rearrange these equations in terms of the Q value. The Q value is nothing but M1 plus M2 minus M3 plus M4, mass of the reactant minus mass of product, or the kinetic energy of products minus kinetic energy of reactants. You can arrange it this way also. Second equation is the conservation of linear momentum parallel to the beam, because linear momentum is a vector quantity, so it has got components along the beam and perpendicular to the beam. So for parallel to the beam along this direction, so you will have the cos theta component along the beam direction and the sin theta component perpendicular to the beam direction. So the momentum P equal to mv, or you can write equal to 2m, with P square upon 2m is equal to E. So P square equal to 2me, or P equal to root 2me. So you can write in terms of this. So for the incoming projectile, it is coming at 0 degree. So you can write root 2m1 E1 equal to initial momentum is root 2m1 E1 equal to the momentum of the ejectile along the beam direction root 2m3 E3 cos theta term, and root 2 m4e4 cos phi. So this is for the ejectile, that is for the heavy residue. Linear momentum is conserved along the beam direction. Similarly, the linear momentum is conserved perpendicular to the beam direction. Perpendicular to the beam direction, there is no momentum for the projectile, so it is 0, equal to root m3e3 sine theta. So this component is sine theta component for the ejectile, and this component for the heavy residue, that is negative sign because it will be in the negative direction. So root m4e4 sine phi. So now these are the three equations, and you can eliminate e4 and phi from these equations to get a relationship between e3, m1, m2, m3, m4 and e1 and theta, of course. So how do? You eliminate. So what you can write this in terms of, so this equation you can write as, here you can write 2m4e4 sine phi equal to 2m3e3 sine theta, and you can write as 2m4e4 cos phi equal to root 2 m1e1 minus root 2 m3e3 cos theta. So essentially what you do, you bring the sine theta, sine phi and cos phi term, e4 phi term on the left hand side, and then the remaining in the right hand side. Now you square and add. So this m4 sine 4, this square, this, when you add them, it will become sine square phi plus cos square phi, that will become 1. So you will have 2m4e4, and then the rest will be on the right hand side. So the result of that will be m3 plus m4e3. You can rearrange the terms, minus 2 m1 m3 e1 e3 cos theta plus m4q plus m4 minus m1 e1 equal to 0. So this is the result of adding. So you can substitute e4 in terms of q and this one. So see here you can replace q equal to e4 plus e3 minus e1 equal to q. So you can write e4 equal to q plus e1 minus e3. So you can substitute for e4 in terms of q, e1, e3. So all you will be left with terms corresponding to e1, e3, m1, m2, m3, m4 and theta. So this equation, if you see here, it is a quadratic equation in the square root of E, energy of the ejectile. And so ax square plus bx plus c equal to 0, where x equal to root of e3, and the solution of this will be the familiar equation. You can write the equation, a solution root of a quadratic equation in terms of ABC. So that is what is I have tried to explain here. The equation which is quadratic in root e3. So what you write, minus b plus minus b squared minus 4ac upon 2a, that is the root of that quadratic equation. But here I am slightly deviating from, you write b plus minus b squared plus w. So b squared, b is nothing but b, and 4ac is w, or other b upon 2a is b upon 2a is b v, and b squared minus 4ac upon 2a is w. So that is how you can write the, and so v equal to root m1 m3 e1 cos theta, and w is equal to m4q plus e1 m4 minus m1 upon m3 plus m4. So now this equation, which depends upon the q value, the q value is inbuilt in this equation, and the e1 and cos theta. So if you want to find out the energy of projectile E3 at a particular angle and for a particular energy of the projectile, you can use this equation irrespective of the mechanism. It can be, it is valid for elastic scattering, inelastic scattering, or any type of nuclear reaction, direct reaction or compound nuclear reaction. So for energetically possible reaction, root of E3 root E3 has to be real and positive. So sometimes there will be situations where some roots are imaginary, so that and negative, so that those roots are ruled out. So based on this equation, you can calculate the energy of reaction products for any angle and projectile energy. In fact, you can also rearrange this equation in terms of the Q value. If you could put Q equal to, then this is called the Q value equation. Q value is nothing but E1 M1 by M4 minus 1 plus E3 M3 by M4 plus 1 minus 2 root M1 M3 E1 E3 cos theta upon M4. So this Q value equation, essentially it is the same equation in a different fashion. It has been represented here, and the solution of the Q value equation, again they are the root E3 equal to V plus minus V square plus W, where V and W are given by these expressions. So this is a generalized solution of the Q value equation, and for any type of equation mechanism, reaction mechanism, you can use the same formulations. Now, when a projectile is bombarding a target, we will go along, we'll see that all the energy of projectile is not available for the nuclear reaction to take place. So certain energy is lost in moving the whole center of mass system, and therefore the discussion of the collisions in the laboratory and center of mass system becomes important. So we will discuss the two scenarios in the laboratory system and in the center of mass system. How does this collisions take place? So in the laboratory system, let us see here. In the laboratory system, the projectile with mass m1, energy E1 and velocity V is moving towards the target, and target is stationary. So if the projectile is moving, the center of mass, which is in the center here, is also moving in this direction. The center of mass will have the mass m1 plus m2 and velocity Vcm. So this is the kinematics of the nuclear reaction. In the laboratory, we will see the projectile is moving with velocity V towards the target, which is stationary. And after the reaction, suppose let us consider the simple elastic scattering. M1 will go at theta and M2 can go at phi. So first let us focus on the incoming reaction channel. So let us set up the equation for the momentum and energy of the system. Before the collision, the momentum is m1v because the target is stationary, and that is equal to the momentum of the center of mass system, that is m1 plus m2 Vcm, because the momentum has to be conserved. So this momentum is same as the momentum of the center of mass system. So this, you can now calculate the velocity of the center of mass in terms of m1v upon m1 plus m2. So this is an important relationship. We will use this subsequently. So in the laboratory, with the center of mass system is moving with velocity m1v upon m1 plus m2, and the center of mass system is moving with the kinetic energy half m1 plus m2 Vcm square. Velocity of center of mass m1v by m1 plus m2, energy of the center of mass half mv square. So half m1 plus m2, this is the mass, into Vcm square. Now you see, you can substitute for the Vcm from this formula. So half m1 plus m2 and Vcm square is written by m1v square upon m1 plus m2 square. So this m1 plus m2 will cancel with 1 m1 plus m2. We are left with half m1v square upon m1 plus m2. So if you write here, you can take m1 common, comma, outside it will be half m1 v square upon m1 plus m2, and this is nothing but E1. So what we have here is that kinetic energy of center of mass, equal to m1 upon m1 plus m2 into E1. That means out of the kinetic energy of the projectile, a fraction m1 plus m2 is involved with the motion of the center of mass. That is called the kinetic energy of center of mass. Now let us discuss in the center of mass system, we will calculate the energy in center of mass system. So this kinetic energy of center of mass system actually is wasted in the motion of center of mass. And what we are going to discuss is what is the energy available in the center of mass system that is useful to induce the reaction. So let us see now in the center of mass system. In the center of mass system, the center of mass is stationary here with the mass m1 plus m2. The energy of center of mass is 0. So VCM is 0 here. So the velocity of center of mass in center of mass system is 0. The mass of projectile m1 velocity will be v minus VCM, where VCM is the velocity of the target. Now the target is moving towards the center of mass with the velocity minus VCM, because we are considering the center of mass to be stationary. The target is moving towards this side, because in the frame of reference of center of mass, target is moving towards the center of mass, the velocity minus VCM. And after the collision, you will find the center of mass remains in the same place. The projectile and projectile and target, or the initial projectile target, move in the opposite direction because the momentum has to be 0. So the bottom line is that in the center of mass system, the total linear momentum is 0 because the center of mass is stationary. So let us write the equation. Momentum of the projectile m1 v minus VCM plus momentum of the target minus m2 VCM equal to 0. So now you can solve this. M1 V equal to m1 plus v2 VCM. So if you see the total momentum is 0, then you can write in this way. And so VCM will be equal to m1 V upon m1 plus m2. So this is the same formula which we got from the laboratory frame of reference. The velocity of center of mass is given by m1 V upon m1 plus m2. Now in the kinetic energy in the center of mass system. Mind you, earlier we discussed the kinetic energy involved in the motion of center of mass. What we are discussing is now the kinetic energy available in center of mass system. So that is the kinetic energy of projectile in center of mass system plus kinetic energy of target nucleus in center of mass system. So kinetic energy of projectile half m1 v minus VCM square plus half m2 VCM square. Kinetic energy of projectile plus kinetic energy of target in the center of mass system. So you can now calculate it. Half m1 v square, it will be, now you can write half m1 v square plus VCM square minus 2 v VCM. So you can write half m1 plus m2 VC square. In fact, if you open it up and you substitute for the VCM from this equation, VCM equal to m1 v upon m1 plus m2. So you can write out. So this will be equal to half m1 plus m2 VCM square. So it is equal to now half m1 v square into, so you can see here, if you calculate this, if you solve this 2, you will find you can put the VCM equal to in terms of m1 v upon m1 plus m2, then it becomes half m1 v square upon into m2 upon m1 plus m2. This is the mass of the target upon mass of projectile plus target. This can also be written as in terms of reduced mass of the system. m1 m2 upon m1 plus m2 is mu, reduced mass, but let's not bother about it. We can write it in terms of m2 upon m1 plus m2 into E1, where E1 is half m1 v square. So here, if you recall, the kinetic energy of center of mass, as discussed in previous one, was m1 upon m1 plus m2 into E1, and kinetic energy in center of mass system equal to m2 upon m1 plus m2 E1. In the previous slide, we derived the expression for kinetic energy of center of mass. That means this much energy tied up in the motion of center of mass, whereas here in the center of mass system, the kinetic energy available in center of mass system is m2 upon m1 plus m2 into E1. So this much fraction of the projectile kinetic energy is available for the reaction to take place. This much fraction of projectile energy is not available for reaction to take place, and that's why it is also called as the recoil energy. Recoil energy means the projectile hits the target and the whole energy is tied up, that some fraction of energy tied up in moving the whole system in the forward direction, or you can say the target gets the recoil to the from the projectile, and that much energy is not available for the reaction to take place. So out of the projectile energy E1, only this much fraction is available in the center of mass system, which will be useful to induce the reaction. So let us see now the energy available in the center of mass system. Just now we discussed mass of projectile and having kinetic energy E1 plus M2 going to a composite nucleus M3 plus M4, where E1 is the projectile energy in the laboratory system, and the energy available in the center of mass system is now ECM equal to initial energy of projectile into M2 by M1 plus M2. This is the fraction of which is available in the center of mass system, and the remaining fraction M1 by M1 plus M2 into E1, that's called as the required energy. So this much energy is not available for the reaction to take place. So in fact, like you call free energy in chemical reactions. The free energy only is available useful energy to induce the reaction. Similarly, here in the nuclear reaction, it is the energy available in center of mass system ECM, that is the useful energy to induce the reaction. Let us try to explain this more details. So again, for this reaction, helium 4 plus aluminium, nitrogen neutron plus phosphorus 30. The Q value we have calculated earlier, 2.425 is the mass of alpha particle. Delta M value, aluminium 27 minus 17.197 neutron mass, and the phosphorus 30. So this is equal to minus 2.642 MeV, which is a endoergic reaction. And now the projectile energy 4.87 MeV, that is the energy of alpha particle available from polonium-210 reaction decay. So ECM will be for this reaction. So when the alpha is bombarding the aluminium 27, ECM will be projectile energy into M2 upon M1 plus M2. Target mass upon projectile plus target mass, and equal to 4.24 MeV. So out of the initial energy of alpha particle of 4.87 MeV, only 4.24 is available to induce the nuclear reaction. That is the meaning of ECM. The remaining 4.87 minus 4.24 is not useful for the reaction. That will go as a required energy, moving the whole system forward. We also discuss in the case of a compound nucleus. Suppose projectile and target form a compound nucleus. For example, here they can combine to form phosphorus 31, and then phosphorus 31 emits a neutron. So the phosphorus 31 will be called as the compound nucleus. So in such cases, what is the excitation energy of the compound nucleus? We also calculated using the center of mass energy. So A plus A, projectile plus target, going to form a compound nucleus. The Q value for formation of compound nucleus, mass of projectile plus mass of target minus mass of compound nucleus. And so the energy available in center of mass is the energy of projectile into that ratio of projectile target mass upon projectile plus target mass. So this is the energy available in the center of mass system, and this is the Q value. So the excitation energy of the compound nucleus. The compound nucleus, let us say phosphorus 31 in this particular reaction, will be formed with an excitation energy of ECM plus Q. Whether Q value is positive or negative, that is immaterial. The compound nucleus will have excitation energy E star equal to ECM plus Q. So that is the significance of the compound nucleus excitation energy, which is governed by the energy available in the center of mass system and the Q value of the reaction. Now, depending upon the type of Q value, it was Q value positive or negative. If there is a positive Q value reaction, then for neutron-induced reaction, there is no threshold. Even the thermal neutrons can undergo reaction. But if the Q value of a reaction is negative, then for neutron-induced reaction also, we require a threshold energy. Neutron should have a minimum energy that is called as the threshold energy of a reaction. So let us consider a nuclear reaction induced by neutrons which is having a negative Q value. So here nitrogen 14, N tritium, carbon 12. So let us calculate the Q value of this reaction. Q value will be mass of the nitrogen 2.863, mass of neutron 8.071, mass of tritium minus 14.950, and mass of carbon 12 is 0. So that becomes minus 4.016 MeV. So this is a negative Q value reaction, means it's an endo energy. So if a neutron has to induce this reaction, then the energy in the center of mass system should be at least equal to Q value. You have to supply energy, otherwise it's a negative Q value reaction. So ECM should be at least equal to Q value. So when we say ECM should be at least equal to Q value, that means minus Q. But this is nothing but ECM, you know, equal to E1 M2 upon M1 plus M2. And so you can write EC threshold energy equal to Q into, you can write here Ma plus Ma upon A. So threshold energy will be, instead of minus Q you write ECM, or instead of ECM you write minus Q into Ma plus Ma upon capital A. So this much additional energy you need to have in the threshold energy. So when we say threshold energy, it is the projectile energy in the laboratory, because the accelerator is giving you, or the neutron that is coming out has to have that much energy in the laboratory system. So when we say threshold energy, that is the energy of projectile in the laboratory. So threshold energy of neutron will be minus Q value, so minus of minus 14 plus 1 upon 14, that is 4.303 MeV. So actually you require 4.016, which is the Q value, but since the neutron will be giving a slight required to the nitrogen 14, neutron energy should be actually more than the Q value by this much factor. And so this is the threshold energy in the laboratory of neutron, which will be sufficient to cause the nuclear reaction. So that is how you can calculate the Q value of nuclear reaction for those which have got negative Q value. Now we will come to charge particle induced reaction. So the charge particle induced reaction, if the reaction is a negative Q value, not only that you have to cross the threshold of the energetics, but you have to also cross the Coulombic barrier. And so that's why for a projectile hitting a target charge particle projectile, then you have to see what is the Coulomb barrier. And the Coulomb barrier for charge particle induced reaction can be calculated Z1 Z2 E square by R1 plus R2. Z1 Z2 are the atomic numbers, and the R1 plus R2 is the radii of the projectile and target. So if you recall the previous lectures, we have dumped this some certain units into 1.44 factor so that the energy becomes in MeV, and R0 is radius constant 1.4, and this is mass number of projectile target to the power 1/3. So now if the projectile has to have this much energy in center of mass system, then only the Coulomb barrier will be crossed. So for a charge particle induced reaction, projectile should have energy equivalent to, at least equivalent to Vc, and so accordingly the Coulombic threshold will be Vc into a factor for center of mass. So Ma plus Ma upon capital M capital A, that is the target mass. So by this much factor, the center of mass energy should be, the laboratory energy should be more than the Coulomb barrier. So for this reaction, again 27 aluminum alpha N phosphorus 30, Vc will be equal to 1.4382 2 into 13 upon R0 A raised to 1 A1 1/3 A2 1/3, so that is 2.584 MeV. And so the energy center of mass should be equal to 2.584, and accordingly the projectile energy in the laboratory will be higher by this much factor, 31 by 27. That means 2.96 MeV. So the Coulomb energy, the Coulombic barrier is 2.584, but the projectile should have 2.96 MeV in the laboratory, so that we have ECM energy available in the center of mass equal to 2.4584 MeV. Now the Q value for this reaction is minus 2.46642. So energetics point of view, threshold should be 2.642 into 31 by 27, that is 3.03 MeV. So now you have a threshold based on the negative Q value, and you have a threshold based on the Coulomb barrier. Whichever is the higher threshold value, that will be the actual threshold. So when it comes to a charged particle induced reaction, if the Q value is negative, then you have to calculate the threshold not only for the Coulombic barrier but also for the energetics point of view, and whichever is the higher value, that will be the threshold. So threshold energy is the higher of the Coulombic and the energetic threshold. So you have to compare the threshold for the Coulomb barrier as well as the negative Q value, and whichever is the higher one will be the threshold for the nuclear reaction. So today we have discussed the energetics of nuclear reaction. What are the Q values? It could be endoergic, exergic, and if it is an endoergic, then there has to be a threshold. Projectile will have some certain minimum energy to cross the threshold barrier. And if it is a charged particle, not only the negative Q value threshold has to be crossed, but the Coulomb barrier also has to be crossed. And accordingly, the energy available in the center of mass has to be calculated, which then the laboratory threshold value is higher than the energy in the center of mass by a factor, that is m1 plus m2 by m2. The factor takes care of the energy conversion from laboratory to center of mass. So I will stop here. In the next lecture, we'll discuss the cross sections of the nuclear reaction. Thank you.